Okay, so let's move on to discuss the linear algebra review that we started last time. So here we go. Let me remind you that we started talking about, so we talked about linear independence. That's sort of the first concept, the set of linearly independent vectors. And from the set of linear independent vectors, we got to this notion of a basis. I guess one of you has their microphone open. If you're not talking, could you mute your microphone? You have some noise. Okay, good. Sorry. Okay, so do you guys hear me still? Maybe in the chat you can say something. Yes, okay, good. So we talked about basis, and so a basis is a set of linearly independent vectors that span a subspace V. So a span, if you recall, was the set of all linear combinations. So the span of a set of vectors, x1 up to xn, is a set of all linear combinations of them. Okay, and so we have a basis for a subspace if the set of vectors span that subspace and also are linearly independent. And we saw, for example, here, this set of these two vectors spans the xy plane, and they're also linearly independent, so they form a basis for the xy plane. And we also saw that this set of vectors also forms a basis for xy plane because they're linearly independent and they span the same subspace. The set of linear combinations is the xy plane. Okay. So one result in the linear algebra, general result in the linear algebra, is that the set of all the bases for a given subspace have the same number of elements. And that common number of elements is called the dimension of V. And sometimes we write it as dimension V. And so in the in the case of this example, we have dimension 2 because each of the bases that we had 2 elements. Okay, so the dimension of the xy plane is 2, which is not surprising. It matches our geometric intuition. And so the dimension also formalizes the notion of degrees of freedom. And then we moved on to the idea of a column space. And the idea is, that you have a matrix, and the matrix has a bunch of columns, x1 up to xp, and each column has n elements. So each column is a vector of size n, x1, x2, and xp. These are all vectors of size n. So they're all in Rn. And we can form the span of these set of vectors. So the span of these set of vectors is what we have defined before, is the set of linear combinations of them, where the coefficients are in Rp. And so the new thing is that we just give this a name, and this is called the column space of X, or the image of X. So the image of X, or the column space of X, is the span of the columns of X. And another point was that I can write this linear combination simply as x times beta, where beta is the vector that contains all beta 1 up to beta p. So here's an example. For example, you have x, which is, let me do this. So this is the x. And so the span of the column space, which is the span of the columns, can be a general element, and it can be written as x beta, which is something like this. And then you can verify that this is in fact equal to this. So each one of these elements gets multiplied by the corresponding column, and then you add them up. So this gets multiplied by that, and the other one gets multiplied by this, and so you add them up. So you get this times this plus beta 1 times this. So that's one way of doing matrix multiplication. So when you multiply a matrix by a vector, the result is can be expressed as scaling each column by the corresponding beta and then adding up the result. You may not have seen this before, but this is a very useful property of matrix vector multiplication. So any question about this so far?
Professor?
Yes. Yes.
On the notation where it says the summation from j equals 1 to p of bj xj, when
Yes.
the arrow points to xj, it says verify as in what? Like, what does that say there?
Verify? What slide are you talking about?
It was this one right here, slide 9.
Yeah.
It says verify as an EX.
Okay. As an exercise, yes. Okay.
Oh, okay.
This is
Verify.
As an exercise, yes.
Okay, like verify that it's what? Okay.
So verify that this side, x beta, is equal to this side.
Oh, okay. Oh, the whole thing. Okay.
Right. So verify this identity. How can I write this? Let me see. Verify the identity. The identity is x beta is equal to sum beta j xj, j from 1 to p. Does that make sense?
Yeah, I'm just writing it down, sorry.
No problem.
Okay, thank you.
No problem. Other questions? Okay, so that's the column space. The only new thing basically is that you can write the span of a bunch of vectors in this compact form, basically, by multiplying. So you form a matrix of the columns, a matrix with the columns being these vectors x1 up to xp, and then a general linear combination is x beta, and so the column space is going to be a set of vectors like x beta, where beta is in Rp. Okay, so another name for this is also the range or the image. As I mentioned, I'm going to use the image mostly. So for us, usually in this course, I'm going to use this notation. But it's also the column space or the range. It's just that many people or different people call the same object different things, and they use different notation. So this image, from now on, I'm going to call it the image, is a linear subspace of Rn. And if you recall what the linear subspace is, somebody discussed this here. So a linear subspace satisfies this linearity assumption. So if you have x1 and x2, when you add them up, they're going to, in V, then when you add them up, they're going to be still in V. And when you rescale x1, let's say x1 already is in V, if you rescale it, it's going to be still in V. So image of X, you can verify for yourself that the image is a linear subspace. It has that linearity property. If you add up two vectors that are in the image, you get another vector which is also in the image. And if you rescale or scale a vector in the image by a number, you get another vector which is in the image. And because it's a linear subspace, it's going to have a dimension, if you recall. So anyone recalls what the dimension of a linear subspace was that we just talked about? Do you want to chip in? Anyone?
It's the number of vectors that are in its basis, or in a basis of it.
Yes, yes. So, right. So what was your, can you maybe, you guys, if it's possible, can you, when you answer or talk, can you give the video so that I can see who's talking also? What was your name?
Alex.
Alex, okay. Hard for me to find people. Okay, let's see. Sorry, this Zoom is a little bit strange. Just decides to, sorry, let me figure this out. Okay, so the dimension is the number of elements in a basis. So it's a linear subspace, and so it has a dimension, and the dimension of the image is called the rank of the matrix. Okay. Have you seen, oh, unfortunately I don't have a poll. I should ask, for example, how many people know what the rank is? Maybe you can do it in the chat. Do you know the rank? Or have you heard about the rank? Maybe yes, no? Yes, okay. A couple of people, yes. Good, okay. So this is just a reminder then that the rank, one way of viewing it is that it's the dimension of the image or the column space of X. So in other words, you can also equivalently, yeah, I already have written it here. So the equivalent way of saying it is that it is the number of linearly independent columns of X. Because by definition, the columns of X span the image. But not all of these vectors are going to be linearly independent. So if you look at the set of all columns, so it could be that the set of all columns of X is linearly dependent. Then we pick the smallest subset. Yeah, then what I wrote is not quite right. So the number of linearly independent columns, it's yeah, that's not a good statement. But so then we pick the smallest subset such that they are linearly independent, and still span the image of X. Yeah, so the problem is that not all of the columns are, so one column could be a multiple of the other column. So you don't need to include both. Or another column can be written as maybe a linear combination of the rest. So you don't need to include that column if you include the rest. So you start to narrow down until you get the smallest subset of columns such that they're linearly independent and they still span the whole the space, the image. So this statement that I have is here is ambiguous. I realize that this is not, the number of linear independent columns is ambiguous because you can form many subsets of the columns that are linearly independent, the key is that you find a subset that's linearly independent and also spans the column space. I'll give you examples. Let me go to give you some examples here. So before talking about the kernel. So suppose you have this. Do you see my screen, or why don't I see on the screen? Okay, sorry, let me check. Something wrong with my. Give me a second. Okay, forget about it. So this is the matrix. So we have a matrix. Let me do it here. So we have, let me do it up here. So I have a matrix X, which is 1, 1, 0, 2, 2, 0. Okay. So think a little bit about this and tell me what. So describe what the image of X is. Okay. So I'll give you maybe like a minute. Think about this and tell me what the image of X is, or the column space of X is. Can you describe it? Okay. And while you think, I'll try to fix my Zoom. Okay. Okay, so anyone wants to comment? Okay, let's see. Yeah. Yes, go ahead.
I was gonna say that it is the span of the two columns, so span of 110 and 220.
Yes. Okay, but that's correct. But what more? Can you say more?
Because X is linearly dependent, because like the first vector is a multiple of the second vector, like 220 is a multiple of 110.
Yes. So
That means that the image is just a line in the XY plane.
yes, okay, so good. So you could say the image of X is X beta, where beta 1 and beta 2 are in R. And this is going to be beta 1, 110 plus beta 2, 220. Beta 1, beta 2 are in R. And we did this before, so this is like beta 1 plus 2 beta 2, beta 1 plus 2 beta 2, 0, and this is like alpha 1, 1, 0, alpha in R. So the set of all vectors, this is the set of all vectors that are in the direction of 1, 1, 0. So it's a line in, as was pointed out, in the XY plane. So if I have the XY plane, this is X, this is Y, this is Z, right? Then the line would be something like 1, 1, and then Z, 0. So that would be this line. And so my image would be this set of everything that's in this direction. Okay, that would be the image of X. Right, and I saw also Brandon in the chat mention, so it would be equivalent. So he said that, which is correct. So image of X, another way of saying it is that it's the span of 1, 1, 0, which is good. So it's the span of, so let me try this. So it's the span, so by definition, it's the span of 1, 1, 0, and then 2, 2, 0, right? But once you do the calculation, or you sort of look at it, because you don't need both of these vectors, so anything that I can write as a linear combination of these two, it's going to be just, as you can see here, anything you can write as a linear combination of these two is just a multiple of this one, or you could use the other one. So it's the multiple of this, so it's going to be just the span of that. Or you could say it's also the span of, equivalently, it could be 2, 2, 0, or any other vector in that direction. Okay, so now what is the dimension of this space? Anyone?
1.
Yes, dimension is 1. And so what is the rank of X?
1.
1, right? Everyone is okay with this? So that's the span, and the rank is 1, right? The rank is the dimension of the image. And you either realize that geometrically this is that, or you would just look at this and see, okay, I just have one vector, and this vector is non-zero, so there's just it's a linearly independent set of vectors. It's like a trivial set of linearly independent vectors, and so because there's just one element in it, the dimension is going to be 1. So that's the basis, and there's just one element in the base. Okay, questions? Let me now grab this and put it a little bit further down. I'm going to do it here. So this has nothing to do with the things that are above it. Okay, so now let's talk about the other subspace associated with the matrix. Question? Okay, so the other subspace, which is related to a matrix or derived from a matrix, is the so-called kernel of X, and the kernel is the set of all vectors that are mapped to 0 by X. So mapped to 0 by X. Another way of saying it is that it's the set of all betas in RP such that X beta is 0. So X is n by p. I'm using the same notation as I used before. So before was X was also n by p. We have it here. So it has p columns, you can see. So X is in Rn times p. So X is in Rn times p. We also have that here again, X is in Rp. X is n by p. So what we have is the set of input vectors that go in and get multiplied by X and are mapped to 0. So the dimension of the vectors are p, so the kernel is going to be a subset of Rp. Okay, so the kernel is a subset of Rp, whereas the image is a subset of Rn. That's the difference. And we also can verify that the kernel is a linear subspace of R. So we have two subspaces associated with a matrix. One is the image, which is going to be a subspace of Rn, the number of rows, and the kernel is going to be a subspace of R to the p, which is the number of columns. And if you think of X as an operator, so operates on vectors and produces new vectors, the kernel is the set of all vectors that under this operator go to 0. Okay. Questions? Yeah, someone wants to add. Okay, let's see an example. It becomes a little bit more clear. So in this example that we had, anyone can tell me what the kernel is. So say, what is the kernel? What is the kernel of X? Maybe think a little bit about, right? A few seconds, maybe 1 minute. Then come up with a description of the kernel. So you can look also at this image. Okay.
If we use the definition of kernel here, and the matrix X times the vector times, for example, beta 1, beta 2 equals 0, 0, 0, we find equation beta 1 equal negative 2 beta 2. So I can write beta X, beta 1, beta 2 as a member in the kernel is beta 1 times 1, negative 2. So
Can you say that again? So we have 1, 1, 0, 2, 2, 0 times beta 1, beta 2.
Equals
right?
0, 0, 0.
Right. So this is the kernel is going to be the set of all beta 1, beta 2 such that this whole, right?
We have
So,
3, 0. Answer is 0,
right.
0, 0.
Right. Okay. 3 zeros here.
Yeah, and the equivalent equation is beta 1 negative, beta 1 plus 2, beta 2 equals 0.
Okay,
We
so
have
I can
just
write this as beta 1 plus beta 2, or beta 1 plus.
2 times beta 2.
Right. Because there are two equations and they're the same. So I can just replace it with 1. Okay.
And exactly mean beta 1 equal negative 2 beta 2.
Okay.
So we can rewrite the vector beta 1 beta 2 as a negative 2 beta 2 or beta 2. Just subspace instead beta 1 negative 2 beta 2.
Right. Okay. So I can write this equivalently as, say, there are different ways. So I can say beta 1 is negative 2 beta 2. And then I can write this as negative 2 beta 2. And then beta 2. Right. And then beta 2 can be anything.
Yeah. And factor out the beta 2 is beta 2 times 2 vector negative 2, 1.
Right, so this can be written as beta 2 times minus 2 and 1.
Yeah, and beta 2 can be any real number.
Right.
The kernel is the vector negative 2, 1.
So the kernel will be the span of this vector, right? Not that vector itself, but the span of a single vector. Right, so the span of this. Right, so if you look at the let's do this. So this is going to be R2. So R2 is going to be the input space to this. And there's no z-axis here. So there's x and there's y. And so this would be, for example, did we make any mistakes, or is this correct? So beta 1, let me check. Beta 1 plus 2 beta 2 is 0. Beta 1 is negative 2 beta 2. You can see it here, right? So this is these two equations are equivalent to this one. And this can be written as this. So the kernel is the set of all vectors that can be written. I can replace basically beta 1, I replace it with negative 2 beta 2, and then factor out beta 2. And so we get this. So the kernel would be anything that looks like so negative 2 here, and then 1. So that would be this vector, right? And then anything in that direction is going to be, that's the kernel of X. Okay, any vector in that direction. And then you can easily verify, at least this vector has to be in our, so at least you have to have like X times negative 2, 1 has to be 0, 0. And then you can verify that this is the case, 0, 0, 0. Verify this. So this vector is mapped to 0, and anything in that direction is going to be mapped to 0 as well. So X times, basically, X times anything in that direction. So if I have multiplied by this times alpha, I'm saying it's, suppose you have a vector alpha and then you multiply X by this. Because alpha comes out, you can see it's going to be equal to alpha. Alpha is a scalar, comes out, and then you get 0, 0, 0. So this verifies it. This is an R. Okay. Any questions about this? So we have the calculation here. This time, actually, we went a little bit further. It was great. So you're fresh, right?
First, yeah.
Fresh, yes, yes. Okay, good. Yes, I guess in previous years, no one has gotten that far. So this is okay. So let's say this, we can write kernel as this, but we can also write it as the span of this, which is nicer. So this is a little bit more informative, writing it like this. Great. So now what is the dimension of the kernel?
The 1.
The dimension of the kernel is 1 because it's just the span of a single vector. And in this case, we have this identity, which later hopefully talk about, or if you have seen rank nullity. So the rank of X plus the nullity. Nullity is the dimension of the kernel. So the dimension of the kernel is sometimes called the nullity. So nullity is 1, rank is 1. They add up to 1. Sorry, they add up to 2. Okay. And 2 is the dimension of the input space. So that's 2. 2 is the dimension of this. 2, 3. So this 2 is this. The rank of the matrix plus the nullity is equal to that. Okay, so now you know about the image and the rank. Sorry, and the and image, the rank, the kernel, and the nullity. Questions, comments? I actually want to ask you a question. So I put the time of the lecture 12:30 to 1:15, but that seems to be too little. I think it should be 1:45, right? Is that true? Has anyone looked up the CC or the MyUCLA or whatever? Yes, okay. So when did we finish last time? Did we finish 1:15? Or 1? Yeah, so I should, okay, good. So I have to fix the website, or the meeting is also, I think I have to fix, okay, 1:45, good. We still have some time. Okay, so good. So what is the next topic? Questions? So we talked about like 2 other bullet points that I had early on. So if you recall, we can go back all the way. So we have talked so far about this, and we've talked about, let's say, span, basis, subspace associated with the matrix. Now I would like to go and talk about the inner product, and then the notion of orthogonality and projection. So have you seen what, like, the inner product before? Maybe in the chat, because I don't have a poll. Inner product? Yes. Just one person has seen it. Yes, okay. 2, 3, 4, 5. Okay. Anyone, so before looking at it, maybe any one of you want to share what you remember about the inner product? You don't want to share?
I'm not sure, but I remember in inner product show us the area we could use computing.
Oh, okay. Yes, that's one way. Yeah. So in the, right. Okay, that's a geometric interpretation, which is interesting. Right. But I'm just, we're not going to use that interpretation, but that's a good interpretation. Yes. So the basic thing to remember is that, yes, it has some interesting geometric ideas behind it, but the basic thing to remember is just a number associated with two vectors. So you assign to two vectors a number. There are other products that give you vectors, for example, or matrices. But for this one, given two vectors x and y, we define the inner product, this is the notation, as the product of the summation of all the coordinate-wise products. So you take the coordinates of xi and you multiply by the coordinates of yi, the corresponding coordinates of yi, and then you sum them up. Okay. What the geometric meaning behind it is, we're not going to worry about too much, but this is a very useful notion. And you can also see that if I write x as a row vector and then y as a column vector, if I multiply this row vector by this column vector, I get the same thing. That's how you multiply two matrices. Okay, so this is like an n by 1, 1 by n. It's like 1 by n matrix. This is n by 1 matrix. The result is y 1 by 1. So you'd write something like x transpose y, and x transpose y is in fact equal to this summation. And so these are alternative way of writing. And then we say that x is orthogonal to y, and we write it as x curve y if this inner product is 0. And this matches your intuition in R2 and R3. So if you have two vectors that are orthogonal geometrically, then the inner product is 0. This the basic example is, can anyone give me a basic example, let's say in R2? What is the most basic example? Two vectors that are orthogonal.
1, 0, 0, 1.
Yeah, so 0, let's say 0, 1, and then 1, 0. So these two vectors, this is like 1, 0. This is 0, 1. Geometrically, they're in like orthogonal, and then you can see the inner product is 0. 0, 1, 1, 0. So the inner product is 0 times 1 plus 1 times 0 is 0. And it also holds for any other sort of choices. Another choice, a little bit more interesting, for example, maybe this. Let's say I have 1, 1, and can you give me another vector which is orthogonal to it?
1, -1.
1, -1, yes. So, okay, you like that one. Okay. So this is negative. I was eyeing the other way. Right? Okay, this is 1, -1. So in geometric, you can see they're orthogonal, and then you compute the inner product. So 1, 1, 1 minus 1. So you get 1 times 1 plus 1 times minus 1. 1 times minus 1, and you can see it's 0. So it matches your intuition. right? And so we write, for example, that 1, 1 is perp 1 minus 1, and so on. So that's the notation that I'm going to use for orthogonality. And so now, questions?
And how about the vector 0 is perpendicular to any
Yes,
vector?
by definition, the 0 vector is perpendicular or orthogonal to any vector because the inner product is always 0. Yes, good. Other questions? So now, suppose we have a subspace V, and the subspace is linear. Again, if you recall what linear means. So linear subspace, and then I want to define what it means for X to be orthogonal to V. So X is orthogonal to V if, and I denote it as X perp V, if whenever, or for any vector V basically in V, so this is saying for any vector V in capital V, X is orthogonal to that little v, okay? So pick any vector in V. So an example is, let's do an example. So I have, let's say XY plane. So V is the XY plane. And then I have, what do I have here? So let's say this is the x-axis. This is the y-axis. So can you give me a vector which is orthogonal to this subspace?
0, 0, 1.
0, 0, 1. Yeah, so that would be this vector, let's say. So 0, 0, 1, which is the unit vector in the z direction, that would be orthogonal to anything in the xy plane. So, so this vector is orthogonal. So let's say 0, 0, 1 is perp v, where v is the xy plane. Okay, so any vector you take here in the xy plane, any of these vectors, this guy is going to be orthogonal to those. Okay, so that's the definition. Okay, so we know what it means for a vector to be orthogonal to another vector, and from this we define what it means for a vector to be orthogonal to a subspace, which, as you can imagine, means that the vector is orthogonal to any vector in that subspace. Okay. Questions? No questions. Okay, now we can define something a little bit more interesting even. So what happens if I take all the vectors? So I have a subspace V, then I define a new subspace, which is called V perp. And this V perp is the set of all X such that X is orthogonal to V. So I collect all the vectors that are orthogonal to V and call that V perp. And it turns out this is called orthogonal complement of V. And it turns out that this is another linear subspace. And so another way of writing this again is if you expand this definition. So this is equivalent to this. So expand the definition. So it's the set of all X such that X inner product with Y is 0 for any Y in V. So let's go back to this example. So in this example, what is the V perp? Can you describe V perp? Can we think a little bit about this? A few seconds. You can also say it in chat.
We have two plan here, x, z, and zy, and we can.
XC and ZY.
No, the intersection between two plan is exactly z axis.
So, right. So what is the V perp then?
It's just the z axis.
Yes, okay, so that's good. Yeah. Why? This guy. I should do this. So
Because Z is perpendicular to the V. I think we can say instead all Y in the V, just we can think about the basis of a space V. And when Z is the perpendicular to or orthogonal to the basis of V, it's perpendicular to all vector in V.
right, that's a good way of doing it. So if you want to find the V perp, you can find a basis for V. So a basis for V would be E1 and E2. So a basis for that space is going to be so E1 and E2. So E1 and E2 is a basis for V. And so V perp, you can equivalently write it as the set of all x's such that x is perp E1 and x is perp E2. If you think about this, it's equivalent. Okay, so if a vector is orthogonal to both E1 and E2, basically to any element in the basis, then it's going to be orthogonal to the subspace. And we see that, for example, E3, this is E3. This is the third basis vector. So E3 is orthogonal to both E1 and E2, and anything in that direction is orthogonal to both E1 and E2. And so anything in that direction has to be in the V perp. But then a little bit of thought also shows that nothing else can be in the V perp, because any other vector that is not in the direction of Z is going to have some component. When you take the inner product with E1 and E2, you get something non-zero, right? So any vector that has a component in the first element, when you take inner product with E1, it would be non-zero. And any vector that has a component in a non-zero second component, then you take inner product with E2, is going to be non-zero, right? So another way of equivalently, so let's say you want to formally formal proof. The formal proof is, so you can write V perp is the set of all x's such that inner product of x and E1 is 0, inner product x and E2 is 0, and so this is going to be x such that, so what is the inner product of x and E1? So if x is x is x1, x2, x3. So what is the inner product of x and, oh, you can't see my screen.
Could you please share your screen?
Yes, okay.
Thank you.
Okay, so what is the inner product of x and E1? So x has x1, x2, x3 component. So that's my x. And so E perp is this. So what is the x inner product with E1?
X1 is 0.
Sorry?
The first one show x1 is 0 and second one show x2 is 0.
Right, so what I'm saying is that this is equivalent to x1. So x inner product with E1 is x1, x2, x3, and then 1, 0, 0. So this would be just x1, right? So the first one says x1 is 0. The second one is x2 is 0. And so I get the vector would be 0, 0, and then x3. And then x3 can be anything. And this is the z-axis. Okay, that's one formal way of proving it. Okay. Questions? Okay, so that's the orthogonal complement, which is very important. Here's another example. So we have x is 1, 1, 1, negative 1. So we know the image is, so what is the image of this? Anyone remembers? If v is, sorry, yeah, v is the image of x, so v is equal to, did we do that? Or?
V is the xy plane.
Yes, v is the xy plane. So what is the v curve then?
The z-axis.
Yes, we just computed it, so it doesn't matter how we started. So whether we start from these two vectors or other vectors in the xy plane, the image is the xy plane. And once we have the xy plane, then the orthogonal complement is determined by that subspace. It's not determined by the basis for that subspace. So this is one basis for the subspace. This is another basis for the subspace. So it doesn't matter which basis you use, the subspace is the same. And so the orthogonal complement is going to just be determined by the subspace itself, not which basis you use. So the orthogonal complement of V is determined by V itself and does not depend on which basis you choose for V. Okay. And so the analysis here is what we did before. So you get that. So then the z-axis is formally the span of this vector. Okay. Questions? So that's the orthogonal complement. Let's see if there's any questions.
Can you move a little bit?
A little bit what?
A little bit up to see your notes. You just write down.
Okay. Questions?
Professor?
Yes.
Yesterday the TA was talking about non-zero pairwise orthogonal. Is that something we should know?
Non-zero pairwise orthogonal.
Yeah.
It doesn't hurt if you know it.
Okay. Can you explain what it is exactly? Because I didn't really understand it yesterday.
So that's what I mentioned in this exercise. You remember that? So I mentioned a set of non-zero pairwise orthogonal vectors are linearly independent. Okay. So it's a good time to. So I was talking about linear independence, but I didn't talk about orthogonality. So now we define orthogonality. So we know what two vectors being orthogonal mean. So being orthogonal means just this, right? So that's the two vectors are orthogonal if the inner product is 0. Okay. So now we say that a set of vectors are pairwise orthogonal. So side note, a set of vectors, let's say x1, x2, x p are pairwise orthogonal if the inner product of xi and xj is 0 for I not equal j. So if you take any two distinct pair, then the inner product is 0. Okay.
Okay.
So for example, this is such set. So these are these 3 basis vectors, right? So they're pairwise orthogonal, which means that this is set of pairwise orthogonal matrix vectors, orthogonal vectors. Why? Because inner product of E1 and E2 is 0. Inner product of E1 and E3 is 0. Inner product of E2 and E3 is 0.
Oh, okay.
Right.
Mm.
Right. So you can see it from here. So this guy is orthogonal to this. Also, this guy is orthogonal to this. And also these two guys are orthogonal. If you take any pair, you get an orthogonal pair. So they're orthogonal to each other. Okay?
Mm.
Sounds good. Other questions? No problem. And so the idea was that instead of pairwise orthogonal vectors, none of which are 0 is linearly independent. So this is an example. So so this set is going to be a linearly independent set because the vectors are pairwise orthogonal and none of which is 0 vector. So that exercise or that result guarantees that this set is going to be a set of linearly independent vectors. And you can, as an exercise, prove it using the fact that use the definition of the linear independence and the definition of orthogonality, let's say. So what you end up doing is that you form a linear combination and then you multiply, you set the linear combination equal to 0, and then you multiply or take the inner product of both sides with each of the elements in the set. I'm not going to discuss it too much. I'll let you figure it out yourself. Okay. So other questions? Okay, so we have seen the inner product, then there's the natural thing that we can define based on an inner product, which is the norm or the Euclidean norm. So the Euclidean norm of a vector is by definition, so the notation is this, and by definition, it's the square root of the inner product of X with itself. And if you recall, the inner product can be written in this way. So inner product of X with itself can be written as X transpose X. So we take the square root of that. And if, again, you remember the definition, it's equivalent to also taking the square root of the sum of the squares of the elements of X. So that's basically X transpose X. So you take the sum of the squares of the elements and then take the square root of the result. That would give you the norm of X. Sometimes called the L2 norm because there are other norms like L1 norm or L3 norm or LP norm. But this is the L2 norm because we're taking the square. We're taking to the power 2. So in this course, we're not going to worry about any other norm besides this. So that's going to be the norm. And this has the usual interpretation of the size of a vector. So if you have like x, y axis, and if you have a vector which is this guy, so that would be 1, 1. So the vector 1, 1, what is the norm of this? By definition, it's going to be 1 squared, 1 squared, and the square root would be root 2. And you know from geometry that that's the length of this. If I have another vector which is just this, that's the E1. Then you have 1, 0 would be root 1 squared plus 0 squared would be 1. And so that's in fact the length of that vector as well. So it matches your intuition of length, but it also gives you a formula, and it also works in more abstract spaces. It works in Rn, like n, for example, could be 10. And it's a little bit hard to visualize a 10-dimensional vector and what the length of that vector is, but this is a nice generalization of that. Okay, and then once we have the questions, So once we have that, then we can define the distance between Euclidean distance between two vectors as the norm of the difference. So the norm of the difference of two vectors is, by definition, the distance between them. And if you plug into the definition above here, so it's equivalent to x minus y, the coordinates are xi minus y, xi minus yi. So you take that and then square it, and then sum of these elements, and then take the square root. That would be the definition of the norm, right? So if you compare this with this, they're basically this. You're using the same definition, but applied to x minus y. And so this is also the kind of right notion. So what is the, for example, distance between so what is the distance between 1, 1 and 1, 0? So we can take the norm of the difference, and the norm of the difference is just the norm of 0, 1, which is just root 0 to the 2 plus 1 to the 2, which is 1. And intuitively, you can see it's just the distance is this, and this is 1, right? So that's the matches your intuition at the distance. So the distance between these two vectors is 1, and you can also verify other vectors as well. But in general, this works for any general two vectors in Rn. And then as an exercise, you can show this very nice identity, which is very useful, that if you square this distance, then it's going to be the norm of x squared plus the norm of y squared minus twice the inner product of x and y. Okay, so this is the vector generalization of the elementary identity. A plus b squared is equal to a squared plus b squared minus 2ab, where a and b are in R. Okay, so we've generalized this to vectors. So as an exercise, just remember that, so let's say int, this is equal to inner product of x minus y and x minus y. Okay, so if I square it, remember, so for example, x squared would be inner product of x and x by this definition. And so here, if I square this guy, you can see that it's equivalent to taking inner product of x minus y and x minus y, and then you expand. So, and then use do this. Goes here. X minus y squared is this, and then use bilinearity of inner product. So search bilinearity in Wikipedia, and you realize what it is. Okay, so the inner product is bilinear. So maybe you don't understand this notation. So bilinearity of inner product. Okay. Questions? No questions? Oh, there is a question. All right, you're right. That was a correction. Great, thank you. Thank you, Menkini. right? Is that your, or Rockford is your last name, right? It should be. So there was a correction in the chat, which, yes. So a minus b squared is a squared plus b squared minus 2a. Thank you. Other questions? Okay, we have a few more minutes, like 2 more minutes. So let's get down to one of the most important concepts that I would like you to learn from this course, if you haven't already learned, and that's the idea of projection. So have you seen projection before? Maybe we can come into, yes. Okay. Good. Yes, no. One yes, one no. How about you other guys? Yes, yes, no, yes, yes, yes. Maybe no. Okay, interesting. Okay, so some people have seen it, some people have not, some people are not sure. So this is a very important topic, and basically it's the geometric interpretation behind linear regression. And I'm going to use it a lot and expect you hopefully to learn or know it by the end of the course. And also very useful in general. So what is the idea of projection? So it combines all the things that I talked about today in terms of inner product and orthogonality. So suppose we have subspace V, and I have a vector X both in Rn. The idea is that I'm looking for the closest element in V to X. So closest element in V to X, and this turns out to be unique. So closest here is a related notion of distance. So distance is the smallest. So what does that mean? It means I'll take a general vector z in V and then compute its distance with X, which is by just taking this, the norm of the difference. Remember, that's the definition of a distance, right? So I'll do that and then try to minimize this over Z. I'll try to pick Z such that this distance is minimum. And an argument here means, I take the argument that minimizes this, not the value. So I take the Z that minimizes the norm of X minus Z. And what I would get is I get what is called a projection. So this idea here is, let me show you maybe the picture. So I have a V here. That's my V. So that's my space. That's the space V. And then I have an X, which is not necessarily in V. And then I'm looking for Z's here that are in V, but whose distance is closest to this. So if I have another Z here, so the distance here is this. This is maybe big. This other Z, the distance is smaller. There could be another Z here whose distance is smaller. So I'm varying Z in V, and I'm looking for the one whose distance is smallest, and that smallest, that vector is going to be X hat. And we're all out of time, but just to mention this and then come back to it next time, the idea is that the vector that has this property, so there's going to be one Z here, interesting Z here, which is, let's say, this guy, and sorry. Okay, so there's going to be one vector here, which is, in fact, the projection, and the projection has the property that that this error, the error vector here, is going to be orthogonal to, yeah, I can't do this, unfortunately. Okay, so there's going to be a projection matrix, sorry, projection vector that's going to be, let's say, this. And it has the property that this error, this this thing E is going to be orthogonal, so that's going to be x hat. And so x minus x hat is going to be, we're going to call it E. This is going to be orthogonal to V. That's the like geometric intuition. So the vector that minimizes this distance has the property that there is the residual or the difference is orthogonal to V. Okay, so that's the basic idea behind projection. I'm going to come back next time and talk about this because we're out of time. I'm going to stop here and see if you have any questions. Questions? Comments?
Also, do you have time to back to slide 13?
Slide 13. Okay, yes.
And
Oh, it takes a while to go. Let's see. Okay, yes.
maybe the wrong the number. Okay. I think the next slide.
Yeah.
No, the next one.
Next.
I'm sorry. Okay. Here you say let x1 and x2 be the two column of x. And the next sentence you say z is orthogonal to v if and only if z is perpendicular to x1 and x2.
Yes.
Is it does it matter x1 and x2 is independent or no?
No, because yes, good question. So it doesn't matter because just verify for yourselves because x1 and x2 are in V. So if z is orthogonal to V, if z is orthogonal to V, then this is certainly true because x1 is in V,
Yeah.
right, and x2 is in V, right. So the question is that whether the other direction is true as well.
Mm-hmm.
And you can verify that this is true because even if they are not, let's say one is a multiple of the other, right? One of these is not necessary, right? So let's say x2 is 2 times x1.
Uh-huh.
So z being orthogonal to x1 is enough, right? The other one is extra. Once z is orthogonal to x1, then z is orthogonal to v. So if I add something extra there, it's okay, right?
Okay, then that show that if z is just orthogonal to one column is enough to be.
Yes, in that case it's enough, but the statement that I've written is correct, right?
Okay.
So z is orthogonal if and only if it's orthogonal to both. But it could be that you could write a simpler statement, yes.
Thank you.
Okay, good question. Okay, other questions? If not, then let's stop. I'm gonna give you my face back. Okay, no questions. See you guys next time. Bye-bye.
Bye.
Bye.